So far, all of the structs that we've defined have only held types that either implement the copy trait or a type that is an owned type, like a string. In those situations, the struct is the owner of its fields, and the fields are the owners of their values. And in general, that's actually a good design pattern because you do not have to worry about references and lifetimes. It's usually pretty easy to reason about your structs if all of the values are owned by the struct. Now, you might be sacrificing some bit of speed by not using references and sharing memory, but the trade-off is usually worth it. With that said, I do want to show you an example of what the code would look like when your struct stores references. So here I have a basic example of a simple struct called train system, and right now it has a name field that is set to a string, and here is our string, and thus the name field becomes the owner of that heap data, and here we are outputting the train system in debug format, and that is what it looks like. So when the struct goes out of scope, its lifetime ends, and the struct is responsible for cleaning up its fields, which in turn deallocate or clean up their values. So this string is cleaned up. So what happens if we define the name field right here to instead store a string slice? In other words, a reference. I'm just going to change this right here to be a ref stir, and you'll notice the program is going to fail to compile. If I just comment out this code right here, you'll notice this is enough of a violation. And if I try to take a look at the error, the compiler will warn us expected named lifetime parameter. So this code will not compile unless we provide generic lifetime annotations, just like we did with functions in the previous lessons. So the borrow checker needs to understand the relationship between this reference and the existence of the struct, which is going to be its owner. We need to use lifetime annotations to state that the string reference will remain valid for the entire existence of the struct. In other words, the struct must be deallocated first before the string slice is deallocated. Because if the string slice is deallocated first, if this piece of data disappears first, then the name field on the struct would become a dangling reference. It would become an address to a non-existent piece of data. So whatever is the referent that the reference is being taken from to provide the value for the name field, that referent must outlive the struct. If the struct of train system goes out of scope, then its data is cleaned up, and then the referent from which its data came can be cleaned up afterwards, and there will never be a dangling reference. Rust needs that guarantee or that statement. All right. So we're going to apply a very similar lifetime syntax for our structs. So right here after the struct name, I'll provide my angle brackets, and then I'll define one generic called tick A. Once again, the name is up to us, and then I'm going to attach it to any reference fields that relate to that lifetime. And of course, we only have one, so I'm going to add tick A right here, and the code is now going to compile. So we are telling the borrow checker to understand the following logic. Consider some generic lifetime tick A, a hypothetical future lifetime called tick A. The struct's name field has that lifetime tick A, and the struct's lifetime must not extend beyond the lifetime of the name field. In other words, the struct and its lifetime cannot exceed or outlive the lifetime of the referent from which name comes from. Once again, if the struct were to outlive the referent that name is a reference to, then the name field would hold a dangling reference. So the train struct must go out of scope first before the data that it is being referenced inside the body of the train struct. All right. So let me show you just a basic example right here. I'll come back to this example. I'm going to move my created string to a name parameter, or name variable rather. And here for my name field, I'll provide a reference to my string up above. So this is a ref string, but that will be deref coerced into a string slice. So notice name and its lifetime is this long, and the lifetime of the NJ Transit train system struct is fully contained within the lifetime of the name variable. All this code and any references to NJ Transit are fully contained within the lifetime of the referent of name that the name field is basing its reference off. Okay, now technically speaking, name is the only field that is a reference, so it's obvious that the lifetime of the struct is coupled to the lifetime of the name field, or more specifically, the referent from which the name field gets its reference from. And maybe in the future, there's going to be an elision rule that allows us to not have to explicitly provide that annotation. But for now, we are stating explicitly that the lifetime of the struct is connected to the lifetime of the name field specifically. So let me show you an example of a failure. Let's now create this name string inside a block. We'll then provide a reference to that string and try to keep our train system alive, and you're going to see it's not going to be able to do that. So right here, I will declare my block syntax. Rust will evaluate that first before it assigns the result to the NJ Transit variable. Here, I'll move my string into the body of the block, and then I'll get rid of my semicolon here to implicitly return the last thing. So take a look at this example. We are creating a heap allocated string whose lifetime is only going to go until line 10. This is the region of code where the name is valid. Then it reaches the end of its scope, or the block, or equivalently the end of its lifetime, and then it is deallocating. We are trying to return a train system struct where the name field is going to be a reference to this piece of data that is going to be deallocated. So for example, right here, if we try to print out the struct in debug format, we're going to try to print out the value of its name field, which is a reference, but a reference to data that at that point will be deallocated. The lifetime of the name string will end, so the field of name trying to reference that data becomes invalid as well. And thus the code will not compile. And you can see right here, borrowed value does not live long enough. Name, our original string, who's becoming the referent that the name field is connected to, is dropped here while still being borrowed. What is still borrowing it? The name field inside the train system struct is what is still borrowing it. And we're trying to access that after the referent has gone out of scope, after its lifetime has ended. So once again, if we move this back out, for example here, now the code will compile just fine, and it's just like our first example. Because now the existence of name first and outside of any specific scope means that its lifetime can now extend to the end of the main function, which means the struct is created after with a reference to this data. The name's lifetime is encompassing or enveloping the complete lifetime of the NJ Transit struct, which is totally valid because njtransit.name, for example, as an alternative here, njtransit.name will never be a dangling reference because that name field is always going to point to valid data, that being the name referent right here, because it was declared first. Then we reach the end of main, njtransit is cleaned up, the struct's lifetime ends first, then the name variable is cleaned up, which deallocates the string that served as the referent from which the name field took its reference from, and there's no point where we have a reference to invalid data. All right, so that is how you declare lifetimes in your structs. Once again, if you are just starting out and writing Rust programs, this is a pretty advanced idea, and I just recommend having your struct fields store either own data or values that implement the copy trait. Don't be afraid to create a copy of a string, for example. It's better to have code that is easy to reason about and make sense before you start trying to optimize for every bit of memory. And furthermore, even when you become more proficient as a Rust developer, remember there's always a trade-off between speed and developer complexity. So if you want to keep storing this as a heap allocated string, so you do not have to worry about the concepts of lifetimes and trying to minimize every little bit of memory by avoiding duplication and just using references, I think that's an ideal, but it's not one that you have to be obsessed about living up to. because sometimes it's just easier to reason about structs if they are simply going to own all of their data, and you don't have to worry about accidentally deallocating a referent from which some struct field is basing its reference on. All right. Hopefully that makes sense. And with that, I will see you in the next lesson.